In this recording, we're going to use a dinosaur example, Procomsognathids, I just learned how to pronounce, otherwise known as compies. We're going to call them compies, these little mini dinosaurs. And we're going to study the normal curve looking at an example of their heights. Let's begin by looking at a graph of the distribution of the relative frequency within this sample. So as we had said before in the previous video, graphs are really helpful. We used a dot plot in that case because our eyes kind of glaze over when we're presented with so much information here, right? 660 in this sample, and there's all these numbers and heights, but this is basically what it is. You can tell sort of what a typical height would be, right? What would be your estimate? Hopefully you would look at it and say, well, it's like right around 34, maybe 33, something like that. 33 and a half, I guess, right between those. And they don't get much smaller than 26 or 41 centimeters, but really typically they're kind of in here between like 30 and 38, something like that, 30 and 37. Sort of a typical height. You don't see too many that are much below 30 or much beyond 37. Okay, so we have a sense based on the distribution, and certainly it looks symmetric, right? It almost looks like it kind of fits this normal curve, which is why we used this example. It's mound shaped, bell shaped even. Okay, so let's study this a little bit. What does it mean to have a relative frequency of 0.136 for a height of 32 centimeters? Well, all that means is that about 13.6% of the compies were 32 centimeters tall. Okay, so it's just a relative frequency. It's not the actual number, although we could have plotted that. 90 compies were found to be 32 centimeters, but it's the relative frequency. The actual number would just be the frequency. Okay, so a relative frequency is always out of one whole. Okay, and we can turn that into a percent. It's a proportion. Next, what's the width of each bar tell us? Well, each bar is a centimeter wide, right? Because the heights are in centimeters and the bars are marked every centimeter. So what does the height of the bar represent? Well, that's just the proportion or the relative frequency of the compies that were that height, right? So we can say, for example, let's pick out a height like 30. Well, it's off my screen a tiny bit, but about 6%, right? 0.06 were 30 centimeters. Okay, so let's just kind of getting a handle on what this graph tells us. Let's proceed. What is the area of the bar that represents the relative frequencies for compies with a height of 32? Well, again, that would just be simply 0.136. And maybe we can just note okay. So the total area of all the bars adds up to 1. So the mean, it says, is 33.5. It didn't make us go through and do that computation, which was kind. The standard deviation is 2.56. Let's go back and check that out. We had thought the mean would be 33.5, right? It seems like it was just between 33 and 34. 33.5 sounds great. Let's mark that. Okay. And the standard deviation being about 2.5. So let's just come out 2 bars and then a half, mark where that would be. So that'd be like 1, 2 bars, and then a half. Let's mark that there. That'd be 1 standard deviation right there. Somewhere in between there would be a typical deviation from the mean. Well, let's go ahead and mark out another, use another color here. Let's go out another half a bar and then 2 more bars. So like from here, and let's mark out half a bar and then 2 more. You might be saying, where are you getting this half a bar and 2 more? Remember the standard deviation was 2.56. So I'm just kind of saying 2.5 for round numbers. So 33.5 is our middle. And our standard deviation is 2.5. So, okay, that kind of looks like, yeah, typically the data fall within 2.5 of the mean, and the mean is 35, which is like a typical height. Compy tends to be around 33.5 centimeters. Let's interpret that. It's important that we can't just do the computations, but we can also interpret them, say what they mean. All right. Now let's mark. We already did mark where the mean was and where 1 deviation above and below were. So what percent of the values are within there? And they said, well, let's call that about 31 to 36. Let's check out how that did with our estimate. Yeah, so they're saying like 31, that's right in here, up to 36. So if I take, you know, that whole bar plus that whole bar, well, what am I going to do with this? It's like half of that bar, right? So, well, what I thought about here is, what if I take this whole one plus this whole bar and half of this one? So if I take half of that, let me see in my notes here what that worked out to be. So half of this is 0.0455. So I'm going to take half of that one. I'm going to take, so that would get me that whole bar, and then half of that bar. Does that make sense? And then symmetrically, half, full bar, and then half of that one. So I want the full bar, and another half. Just draw my little arrow down there. I want half of that. So all those numbers that we're going to be adding up are these. I'm going to take half of those and then those full bars. So again, the half, and then the full bars. Now we'll just make a little note here. Okay, so I'm going to use half of the proportion for each of those. Let's do some addition. Add those all up. It works out to be 0.667, which I can just say it's about 67%. Okay. So that's within 1 standard deviation for this kind of bell-shaped curve. It's about 67% is within 1 standard deviation. Well, let's go out 2 standard deviations now and see what that does. Okay, that's actually going to be most of the stuff. So if I were to do this, I could either add up a whole lot of stuff, all in the middle here in the green, or I could simply say, hey, you know what? I just want to take the part that's outside. I want to take those and add up just what's outside and subtract from 1, right? Because we established before the whole area is 100% or 1.00. So I'm for doing easy work, not hard. So let's do 1 minus that little bit times 2, right? Because you can see it's 0.018, 0.008, 0.002. It's the same thing. So let's take 2 of those. Let's do 1 minus 2 times, and then the stuff that was outside, the 002 plus 008 plus 0.018. Do some math there. I believe it works out to be 944 would be the part in the middle. And call that 94%. 94% is a decent estimate here. So we got 67% within 1 standard deviation, 94% within 2 standard deviations. Turns out that's really close to what we're going to see in like a perfect normal curve situation. As you can see, this data was really nice and symmetrical and bell-shaped. All right. So let's proceed with the final couple questions here. Draw your smooth curve over the midpoints of the tops of the bars and describe that shape. We can do that. Again, I'm shooting for the midpoints. All right, so there's our smooth curve. Describe it. Well, it's a bell curve. It is a smooth, symmetrical mound shaped, bell shaped, okay? Those are the words we use. Okay. So shade the area that represents 1 standard deviation. Okay. So if I were to do that, we've already kind of put our check mark. So let's just do a little shading here. And say how would you answer, how tall was a compy? And what you could say is simply, a typical compy is between 31 and 36 inches. And I think I had said inches, it's actually centimeters. Okay, so this is a nice lead-in to what we're going to talk about soon, which is the normal curve. And what you can notice here is this is on our next page, the typical or perfect normal curve, where 68% of the data fall within 1 standard deviation of the mean. Ours was 67. 95% of the data fall within 2 standard deviations. Well, ours was 94%, wasn't too far off. And then if you wanted to go out 3 standard deviations, it would be 99.7% of the data. So this is our empirical rule, and this is something that we're going to be using next class, the 68, 95, 99.7 rule. Okay? 68% within 1 standard deviation, 95% within 2 standard deviations, and then 99.7% of the data, pretty much everything, right, is within 3 standard deviations. Thanks for watching.